Okay, in this video segment, we're going to talk about nuclear reactors and kind of how they function, and then get into a little bit about how we deal with the waste that comes from nuclear reactors. Okay, so nuclear reactors, all the reactors that we have in our world are fission reactors, which means we're splitting the atom to do that, and we mainly use uranium-238, I believe, as our core substance in our nuclear reactors. So we're going to start by watching this little video on nuclear reactors and kind of how we led from the atomic bomb into that.
In July of 1945, the United States Army assembled some of the world's greatest physicists in the New Mexican desert at Los Alamos. Armed with an understanding of chain reaction and Einstein's famous phenomenon, E=mc², the goal was to create an atomic bomb before the enemy. In a short time, scientific theories were turned into something of enormous power when the United States dropped nuclear bombs on Hiroshima and Nagasaki. More than 100,000 people were killed in Hiroshima alone. The atomic age had begun. After the war, scientists hoped to use nuclear power at home, this time harnessing the power of the nucleus for cheap, clean energy. By 1951, scientists and engineers had taken the same technology that destroyed Hiroshima and Nagasaki and used it to generate electricity.
It was a very exciting field. We thought it would be the leading method of making electricity throughout the world. You have a very small amount of space, 12 feet tall, 12 feet in diameter, and you produce enough electricity to run a large city in that small space. So the energy source is extremely concentrated, which is one of its great benefits.
The principal element used in nuclear fission is uranium-235. Before the war, scientists discovered a special property of this particular isotope of uranium. When a neutron strikes the nucleus of U-235, it causes the atom to fission or split, releasing more neutrons that can split other uranium atoms. Each fission releases large amounts of energy. By making small pellets containing uranium-235, loading them into fuel rods, and putting them into the nuclear core, scientists are able to create a self-sustaining chain reaction that produces enormous amounts of energy. This energy is used to heat water, which produces steam, that drives turbines, generating electricity. 20% of the electricity consumed in the United States now comes from nuclear power. But debate continues about plant safety and the risks associated with transporting and storing nuclear waste.
Okay, so that's kind of a brief intro into the actual nuclear reactor and kind of where it comes from. Now, the reactor itself actually consists, on a basic level, of 3 closed loops. Okay, so they're all water-based loops, where you have the pink loop of water, the blue loop of water, and the green loop of water. In the pink loop, this is where the reaction runs. This is where your control rods are at. This is where you're actually controlling this experiment and making sure that it runs on a safe pace. So what the control rods do, the control rods basically absorb neutrons. Okay, so the fuel rods would run uncontrolled if it wasn't for these control rods. What happens is those fuel rods are constantly reacting, constantly making extra neutrons, and this would be an exponential growth in terms of the reaction speed. However, the control rods, they have material in them that can absorb neutrons without reacting. So they space control rods throughout the fuel rods. So some of the neutrons that come off of the fuel rod goes into the control rod, which then absorbs that neutron and slows the reaction down. So the whole idea behind that is the control rods are absorbing neutrons. They don't actually change the speed of the individual reactions. It just limits the amount of neutrons that are available for the reaction to happen. Now this loop is at high pressure and it's full of water, so you have high pressure water, high temperature, so it does not boil. However, that water then pipes through our second loop, which is the blue loop, that isn't under pressure, And so the extra hot pipes here can boil the water in this loop, creating steam. Now this loop is where the electricity comes from. The steam passes through the turbines, which then spin generators and then in turn create electricity. Now this steam has to be recycled, so the steam then passes through the turbine into another tank where there's cooling rods, or there's these cooling pipes, which it recondenses down, becomes a liquid again, and it gets pumped back in and redoes the whole system. This water out here never enters the actual containment structure, and this is just water that keeps getting pumped through into our cooling tower, so this steam can be then recondensed. Okay, so those big gigantic towers you see, kind of the notorious nuclear power plant towers, really that's just the last piece of the puzzle, where those towers are just gigantic pools of water that are letting off steam and venting out to cool that water down, and then they recycle that water also. The idea is they want to reuse the water and not pump it out, because any of the water that's part of this system does have some radioactivity to it. Primarily the water inside, but even this water has a little bit to it that we don't want to expel into our environment. Okay, so that's the basics behind a nuclear reactor. Usually at any nuclear facility, there's several of these, 2 or 3 of them running, and they kind of turn them on, maintain them, and that kind of stuff as they proceed. Now, we haven't really built a nuclear reactor in our country since the late 70s, I believe. So a lot of this technology is pretty old in terms of what they do. Obviously, they've been updated and maintained throughout the years, but there is some pretty cool new designs for brand new nuclear reactors. Your textbook actually talks about one of them that's pretty interesting. So maybe take a minute and read up on that one. Now, when we deal with these fission reactors, there's 2 things that we have to worry about. One is making sure that the actual reaction run's controlled, so we don't have accidents. Part of your research that you're going to be doing in this unit is to look up a couple of the different accidents that have happened and actually research why they happened, what caused them, and what's the result of that. The other thing we got to worry about is waste, because anytime we do a fission reaction, those daughter isotopes are radioactive, which means they're still, emitting radioactive waste, gamma radiation, beta radiation, and we had to somehow contain them and keep them safe from the people and the animals around. So what we do is we store those used fuel rods, once they get used up, in 12-meter deep tanks. They sit there for over a decade, and they had to sit there so long because they're still reacting. Okay, we take them out of the plant once they become inefficient enough to run the power plant, but however, they're still reacting and they still get hot. So we put them in water, so the water helps cool them down and helps to distribute that heat, and then also the water acts as a shield for that radioactivity that's being let off of those. The problem is this: once your plants start to fill up, people want to move these things off-site to storage. Now, we have done that, and we store them in what we call deep burial sites, hundreds of feet down, encased in concrete type of sites. The problem is not very many people want nuclear waste traveling down our highways, and not very many people are thrilled about having a burial site anywhere near them. So there's lots of politics, lots of red tape, there's lots of issues with trying to get a place to move this to and store. Lots of times students ask about, what about sending it into outer space or Antarctica, or putting it in the bottom of the ocean, those kind of questions. And all of them are viable options if we had the money. The reality is, the reason why we do most of the stuff we do right now is that nuclear power is actually a cheap energy source for us. And until it becomes more expensive to store it in our current locations, we're probably not going to do much about it. Because sending it to outer space, all the weight that would be there, transporting it even to Antarctica, or trying to do something at the bottom of our oceans, all those things have enormous amounts of cost involved with that, because you're moving such dangerous material. And in the case of outer space, it's so heavy, just to get it up there and out of our solar system would be a very expensive type of task. Plus, I don't know if we're solving our problem, because this stuff is going to sit around for 20,000 years before it is safe to handle again on a day-to-day basis. So just putting it someplace else for 20,000 years may not be our best option as we move forward. So that's one of the controversies with nuclear power plants, is what to do with the waste. Now, there is another type of waste. It's called medical or industrial waste. We give it the designation LLW, which is low-level waste, and HLW, high-level waste. The LLW stuff is like the X-ray films, the containers that had radiation drugs in them, the leftover chemotherapy drugs, industrial films, that kind of stuff that may have some radioactive properties to it. This stuff doesn't get buried in the deep burial sites. We can dispose of those in a low-level burial site, like a landfill. Now, not just any landfill works. You have to be a certified landfill, a company that's gone through the process of properly disposing of these radioactive waste at their site. So there's two different levels. High-level stuff is your fuel rods. That's nuclear power plant stuff, and then the low-level stuff, which is a lot more low-level than there is this that we deal with in terms of our waste. All right, that brings us to this idea of fusion. We're going to do a different segment on fusion, so we'll stop here, and then the last segment will be about fusion. Thank you.